Thank you all for coming to another systems engineering seminar. My name is Andreas Malikopoulos. I'm faculty in the Civil and Environmental Engineering Department at Cornell and also affiliated with the Systems Engineering program. Today I'm delighted to have Professor Michael Kokkolaras giving us a seminar. Dr. Michael Kokkolaras is a faculty in mechanical engineering at McGill University and the Associate Dean for Faculty Affairs at the Faculty of Engineering. His research interests lie in the broad area of computational engineering that includes multidisciplinary, derivative-free Bayesian optimization, digital twins, automated machine learning, among other topics. He is a fellow of American Society of Mechanical Engineers, an associate fellow of AIAA, and an elected member of the ASME Design Society. He currently serves as the publication chair of the ASME Design Engineering Division and on the board of on the advisor board of the ASME Journal of Mechanical Design. He has served in the editorial board of all the flagship conferences and journals of the design optimization and has received numerous awards, including the ASME Design Automation Award, the University of Michigan College of Engineering Outstanding Recent Scientist Award, and the ASME Journal of Mechanical Design Editorial Choice Award. With this, please join me in welcoming Professor Michael Kokkolaras.
Thank you, Andreas. I really appreciate the kind words. I really appreciate you memorizing my bio. it's really heartwarming. It's me who thank you for the invitation to come here and give this talk. It's a pleasure. You have a wonderful campus, and I've been really lucky with the weather, and I have enjoyed every minute of my visit so far, so I am the one who is thankful. So, before I start with my talk today, I need to give credit to the people who have done the hard work. I've been blessed with really wonderful graduate students and postdocs, and my overview work today is going to include work that they contributed to. In fact, that they carried out mostly. So I want to talk today about some of the computational engineering design challenges that we are facing when we're trying to develop and optimize what is known in the community as complex systems. I was never really at ease with this term, but it does reflect the fact that these are complicated problems of high complexity. It depends on how you view complexity. There's different definitions in different fields, but what we're trying to say is, in very simple words, these are not easy problems to solve. Okay? And some of the challenges, only some of the challenges, include complexity and dimensionality. And when I talk about complexity here, I mean how do the subsystems comprising a system, or at a higher level, systems that comprise a system of systems, interact with each other. And as we say in the community, how tight is this interaction or the coupling among them? Then we have dimensionality. We have vast design spaces, not only in terms of dimensions, how many dimensions in which space are we talking about, but also in terms of size. So these are the first couple of challenges. Then we have to deal with the challenge that the requirements for which we design systems, and actually it's a whole different question where these requirements come from, okay, may change over time, especially when we consider systems with very long life cycles. For example, as you're going to see later, an aero engine in operation as part of an aircraft. And finally, we have the eternal trade-off between the predictive capability of our models that gets higher and higher, but also the computational cost. And this is like us, trying to catch our tail, because the more computer power and more computer capability we have, the more complicated the models are that we have, and the more time they cost to solve them. I want to start with some preliminary stuff. There is still, from what I see, in meetings and conferences, a bit of confusion between multi-objective and multidisciplinary. Some folks still use the two interchangeably, and I want to make sure that we understand that they are not the same thing. In a single disciplinary analysis, you have some inputs and you have some functions, what I call functions of interest as outputs. And they can be different, of course, objectives that may be conflicting, but you only use one single discipline to compute them. The most trivial example, structural engineering, and you're computing things like masses, stresses, deformations, and this can be conflicting, of course. In multidisciplinary optimization, you still have multiple objectives. But to obtain these multiple objectives, you have to execute different multiple disciplines that interact with each other. And these interactions are not an easy thing to deal with. Okay? In fact, if we can think that you can actually put them in a black box, all right? So pretend you don't see what is happening in there. You just plug in an input X, and you're able to get your multiple functions as a function of X, right? But inside, there is this multidisciplinary analysis going on. And if this multidisciplinary analysis converges, which may seem like a trivial thing to you, but trust me, it's not, okay? Then everything is fine. You should consider yourself lucky. You couple this with an optimization algorithm that tries different nexus to optimize the Fs, and eventually you will converge to some solution. But when this does not happen, and in the vast majority of the cases for really tough problems, it does not happen, then we use optimization as a tool to make it happen. And I'm going to, of course, elaborate in a little bit. So let's take a look at the most simple problem that you can have, but still it features the important properties of the problem. You just have two subproblems, whether they represent difficult physical components or different physical systems, or whether they represent disciplines, it's irrelevant. What is relevant is that the output of the one is an input to the other, and they may also share independent variables, right? But because they have their own objectives, and they may not agree on what these shared variables should be. Notice these are independent variables always. And also, this may want an A of a certain value, but this A is not an independent variable. It's a dependent variable from problem one, and vice versa. So this is the simplest one, and I'm showing it and using it for illustration purposes. In reality, you have tens, if not hundreds, of subproblems and thousands of interacting variables. So the remedy has been, as always, divide and conquer. Right? You separate this, okay? And when you separate it, you need to introduce auxiliary variables. So you have local copies of the linking variables. You have a local copy for A, local copy for B, and local copy for U, etc., etc. Now you can solve these problems independently, okay? And this has advantages because you can use different optimization algorithms, etc., etc. You also learn more about the individual problems, but you cannot forget that they are linked in reality. So you need to, after introducing the local copies, you need to formulate consistency constraints for these local copies. They have to agree. You cannot forget that they have to agree. And then, instead of trying to deal with this numerical, with these equality constraints numerically, which is extremely tough to do, what we are doing, we are relaxing them, as we say in mathematical optimization, using a penalty function approach, specifically an augmented Lagrangian penalty function approach, that has a linear term. Remember, CI computes the inconsistency. You want the CI to be 0 at the solution, and a quadratic term. For the ones of you who are a little bit more well-versed in optimization, these linear term coefficients are the Lagrange multipliers of the consistency constraints. And then we use a well-known result in nonlinear programming. This is not something we developed. It's the alternating method of multipliers, which updates these important coefficients here, the V's and the W's, as you solve iteratively all the subproblems independently again and again. So you sweep through all the problems, then you exchange information, you update the parameters, you do it again. And remember, you have a penalty function for each variable that is linked and needs to be coordinated. So this can get out of hand. It can be a very large and a very tough problem to solve numerically. Going back to our example, like I said, we have coupled and shared variables. In this case, we need for each subproblem 3 penalty functions. Okay. I'm omitting here, but of course you can have also extra local design constraints. And you solve this iteratively until it converges. And it will converge under standard smoothness and differential, convexity assumptions. Now you'll tell me this does never apply in real life, and I'll tell you yes, I agree, but it's better to have an algorithm that has theoretical properties than nothing. So it will work. It will need some help sometimes, but it will work for many, many applications, and we have used it in many, many applications. And to my knowledge, if I may say so, it's the only distributed optimization, multidisciplinary optimization algorithm or technique that at least has theoretical properties of convergence. Now, we also developed tools both in MATLAB and in Python for releasing the user from the need to formulate and implement and do all the bookkeeping, these penalty functions. So we're asking for a simple thing. For a simple problem that we have, we're asking them to just give us the structure of the problem. So you have 2 subproblems. You have the local variables and the global variables and their local copies, and where they belong, and with which other variable they're linked. If they're linked, if they're not linked, you leave this empty, and if they're an output or an input in the case of dependent variables. So for the simple problem, that's all you have to give. For a much more complicated problem, you just have to give the analogy of this. And then we segregate the disciplinary analysis from the penalty function, and I don't need to tell you here the details, but we use some computer science approaches to concatenate everything in one big vector, and we apply this, and you just need to provide the computation part, how you will compute the y of x given an x. And our algorithm, our technique rather, will do all the rest. So this is downloadable at GitHub for free, and it has also examples, and you can use it if you like for your programs. We conducted an empirical numerical study of how these things compete. And what I want to emphasize here is that when you solve all the subproblems, you spend computational effort to solve the subproblems. And we represent it here with this ni, which is the number for the internal loop iterations. But then, like I said, you have to do this multiple times, and we denote that with no, the number of outer loop iterations. And for a specific example that we have, we did a numerical study with many examples and many runs, and we have published this. We realized that it turns out, we cannot generalize it and we cannot prove it robustly mathematically, but empirically, it turns out that it's better you come down to very small consistency constraint values, practically 0, very quickly, at a small cost. These are the function evaluations that you need to pay. When you actually solve the inner problems at a very low accuracy, but you do it many times. And if you try to solve the inner problems at very high accuracy, but overall very few times, you get much, much worse results that are here. The possible explanation of that is that, especially at the beginning, the algorithm is not in areas of optimality. So you do not want to spend too much computational effort to get very highly accurate optimization subproblem solutions when you're not overall in a good area, especially because the feasibility that is necessary for the consistency constraints has not started to kick in because the penalty functions have still relatively low parameter values. Okay, switching. Let's go now beyond one system. That was for an aircraft design problem. Let's assume for a second that you are a regional airline. I operate in Canada, so I had to use a Canadian example. And let's say that you want to expand to a national network. You have several questions that you have to ask yourself. First of all, you will need new aircraft. Hypothetically, you're expanding, so you need to serve more airports. You will need additional aircraft. You need to increase your fleet. Then you need to figure out where are you going to fly and how are you going to connect all these airports, and on top of that, how are you going to allocate your existing fleet and the additional aircraft to these new routes. So this is a problem that we considered as a system of systems problem in an approach. In fact, when we did a literature review, it was already presented as a system of systems problem. Okay? And what was happening before, in the previous work that we studied, it first of all assumed that the networks between the airports were fixed hub-spoke networks. So this is the typical paradigm in the industry. You keep flying only from large airports to large airports, and then you serve regions with connecting flights. So they assumed that this is the way to do it. And they also fixed the aircraft range, because you also have, when you develop, when you want to add new aircraft, perhaps you cannot just buy off the shelf from the manufacturers. Perhaps you have a say. You know, it's a competitive world, so you can tell them what you need and they can develop it for you. So we did not assume fixed aircraft range. The previous methods used all-in-one computation. Again, they were bundling everything together. They were hoping to converge and get solutions, and that was not happening too much. And therefore, computationally, they were limited to 7 airports. Now, I'm not claiming that this is the real state of the art, because probably airlines do it, but in a proprietary way, and perhaps they do it better. But that's what we could find in the engineering design literature. What we did is we formulated a distributed optimization problem. It's actually a hybrid distributed versus nested formulation, where we start at the very high end. So DOC stands for direct operating cost of the fleet. And we want to ask, for the new aircraft that we're going to add, what are the main variables? Well, its range and its capacity, how many passengers it can carry. Once we have this idea of what is the range and the capacity for the new aircraft X, we pass it as targets for the aircraft design problem for that new X, aircraft X. Once we have optimized the aircraft for its optimal direct operating cost, then we can feed it, and of course also with the number of it, to the network. Configure network means where am I going to fly to where and how, and we left the algorithm completely free. They could connect any airport to any airport. And once you have the network, you have a nested problem with allocating the aircraft, and how many of those, to the network. Okay? So that's a high-level formulation. The details I would be very happy to share with them in the paper with you. And once you have all this done, then you can actually complete the direct operating cost of the entire fleet, not just the one aircraft, and you close the loop. And this iterates. Now, these are tough problems, all of them. Okay? Especially this nested problem, because it's a mixed integer problem. Now, let me show you a picture. If you close this in a black box, this is the response surface you get from a design of experiments. This is the capacity, and this is the range. And if you try to execute all the rest, this is the direct operating cost for the fleet. This is a nightmare response surface to optimize on, especially with gradient-based algorithms, right? In addition, you have all these white spots. These white spots are areas where this procedure here failed to return a value, failed to return a DOC F value. So I'm showing this just as a small illustration to tell you that this is numerically a very tough problem to solve. So this slide was presented by Simonis from the Boeing company 15 years ago, and at the time, officially, they claimed that their largest challenges with aircraft design were long runtime of the models, and we're not talking about 15 years ago, right? Things are not much, much better. They're better, but not that much. Memory requirements, we can scrap this off. It's out of the scope and taken care of, because nevertheless, there is a lot of progress in 15 years. Software might fail. Anecdotally, Simone said, there's no, of course, record of that, but orally, he said at the conference, I happened to be there, it was an AIAA conference, 80% of our simulations do not return us a value. Okay? So this is a big issue. You don't necessarily have derivatives. We're going to talk a little bit about it more later. And okay, this is standard challenges in numerical optimization. You may have local optima, that's fine. I'm not going to go into it. And your functions are not necessarily smooth. These are somewhat related, of course, right? Because you cannot have gradients in that case. So anyway, for that reason, we considered the following flowchart. There is a huge amount of work and a fantastic mathematical framework on gradient-based optimization. Right? Then you'll ask me, why is there so much work in heuristics and derivative-free optimization? Well, because we have to ask ourselves the fundamental question. Are there gradients? Right? This thing here. Now, do the gradients exist theoretically? Because in all the models that you develop and you use, you're trying to capture an underlying function, mathematical function, right? Now, this mathematical function, what kind of properties does it have? Theoretically, is it continuous? Is it differentiable? That's the first question. If yes, well, if no, then you have black box optimization. It means you know nothing about your model and you cannot assume any properties or any structure. You have to go to black box optimization. And that's the difference between black box optimization and what you're going to see later as derivative-free optimization. These are two different things. If you can assume with certain certainty that you have gradients, can you compute them? Either exactly or by automatic differentiation or what have you. Now, if no, then, well, sorry. If yes, then you use gradient-based algorithms, period. Derivative-free optimization algorithms are not competitors to gradient-based optimization algorithms, right? They're there if you cannot use gradient-based algorithms. So, easy answer, use gradient-based algorithms. If you cannot, if they're not available numerically exactly or through automatic differentiation, can you approximate, but can you approximate them with reasonable cost? What do I mean? Well, many people say, okay, I went to a point in the design space, and I spent some time there, I did some finite step, if I used finite differences or any other methods, complex steps, whatever, I did some numerical study and I approximated my gradient well. I said, excellent. What if you go to this point? And what if you go to this point? You have to do this again and again and again. So can you do this at reasonable cost? If the answer is yes, then again, you go to gradient-based algorithms with approximated gradients. And if no, then you have to go to derivative-free optimization. Okay. That's extremely important in my opinion. That's why I really emphasize this slide. So we do use derivative-free optimization because many of the times in our flow charts we get here or here, many times. So I had the big opportunity to collaborate with both of these persons a long time ago, more than 20 years ago. And I have since continued collaboration in the sense that I'm using their algorithm and they improve it based on my problems, etc., etc. So it's called mesh adaptive direct search. It has the unique structure of consisting of two steps, this algorithm. The first step is optional. You can skip it if you like it. And it's completely user-defined. The user decides, in the first step, I'm going to try some points, either by using a heuristic like a genetic algorithm, or because I like some points. I know something about my problem and I want to try some points. Or I'm going to do a huge DOE, or, including I'm going to do nothing. Then there is the mandatory poll step that, based on positive spanning theory, creates directions in the design space and tries points, and this is where the convergence properties come from. It uses Clark's non-smooth analysis. Now, the software package is one of the best public available software projects I've ever seen in my life. It came close twice to winning the Wilkinson Prize in software. Extremely well supported, and it's free. So if you're really interested in ever trying a derivative-free, rigorous derivative-free algorithm, you should really go and check it out. So we solved this, I don't want to go the slides back, excuse me, this very, very complicated problem we had with distributed optimization using the mesh adaptive search. And this is just a sample of results we got, right? So this shows graphically which airports are connected to which. They're not all of them, but many. This is, we had, by the way, we solved the 7-city problem to match the literature, and then we were able, with our approach, to go up to 50 airports before we got into numerical problems. So we more than doubled what could be solved. So here you have the additional aircraft sample of results. And of course, here I'm violating one of my presentation rules. And you know, if I were one of my students, I would scold them after that. You know, you never show these digits, right? It's not important whether it's 8, 9, 2, 5, 4, 6, 6, right? But that's the number. What I want to focus in that if we had taken the fixed hub-spoke approach and choose Calgary, for example, as a hub city, or Toronto, the approximate cost would be 9 million and 13 million. And again, it depends on how accurate our models are to compute this. But I see everything from a relative point of view. I don't see them from an absolute point of view. With our approach, the direct cost for the fleet is in the order of 5.5 million, which is, again, regardless of how accurate these predictions are, relatively, it's a much lower number. Okay. Again, there's more and more details in the paper, of course. So we were happy that we could improve using these derivative-free optimization techniques and distributed optimization techniques. Changing gears again, okay? So, changing requirements. I mentioned earlier on the example of an aero engine. So, there's something called a turbine rear structure, and for some crazy reasons, I never actually investigated why, for aero engines that are mounted on wings, not on the fuselage, but on wings, the mounting is happening at the end. And so this is the component that mounts the engine to the wing, but also the component that is the most thermally loaded because it's the end of the aero engine. Right? So you really do not want this component to fail, especially when you're flying. Now, the loads can change depending on how the engines are operated, especially as they wear down over years and years. Or the loads can change if suddenly the supplier of the TRS needs to supply to a new developed engine. And it's business considerations get in the game there too, because a supplier makes profit by, does not make profit if they redesign and remanufacture all the time the components for every time GE or Pratt & Whitney or Rolls-Royce change their engines. Right? So it's a big deal for them to figure out how can we design a component that can perform under different requirements. In this case, in this example, under different thermal loads. So you don't want to throw them away every time they're not adequate. Sometimes you get help, and advances in additive manufacturing provided here an opportunity of using additive manufacturing technologies to redeposit a stiffener along the circumference of the structure, and therefore, from a structural integrity point of view, reinforce it. Okay? So let's take a look. These are the 4 areas where the loads can change. And then you can have stiffeners that are deposited in different shapes or concepts here, the wavy concept, or the hatched concept, or the tubular concept. And these are just different choices, but these are designer choices, right? And then, once you decided which choice, then the sequence of the manufacturing, of the additive remanufacturing deposit can be like this, and then another deposit, and then another deposit, so you can come up with the hatched concept that I showed earlier. The bottom line here is that you have to make a lot of decisions, okay? And it's not an easy problem to solve. let's take a look at a two-dimensional projection of the parameter space. So we're looking at the thermal loads T1 and T4. Let's say we have a proxy or a metric for what is safety, these isocontours. So the higher the better. You want to be here, you don't want to be here. And then we came up with some terms, sometimes following the literature, sometimes inventing our own. You have the capability of the current design, which means here the design is capable, it's high safety. If you think that this is your boundary of where safety becomes questionable, here's where you're not capable, right? This is not an area you want to be. That's why it's hatched. Shaded, sorry. Then you have the requirements, and let's say the requirements are easy. You have to be within this green box. If you have to be within this green box, you realize that the area of capability is small. So this is your buffer. These are Monte Carlo simulations, right, of where you are. And most of the Monte Carlo simulations are not in a good area. Okay? So this is the dangerous area. But you also have the excess area. You have this area here where you don't need to be because your requirements are in this box here. Right? So these are just terms that we need to use. And like I said, we use Monte Carlo to compute the reliability of the design under these conditions and these requirements. So once we go to our hatched concept, we find out that for this simulation, reliability is quite low, 0.3%. 30%, it's 0.3. The excess is quite large, and the weight, because weight is the driver of design in aerospace, right? Every single gram matters a lot. Now, we can, we can deposit more material, right? Under the same requirements, and by doing so, we're shifting the safety. So now we have a smaller area of non-reliability. So we increase reliability to 0.76%, so to 76%. But we also increase the excess and the weight. This is just an example. I'm not optimizing here yet. I'm just trying things out, right? So we came up with what we call design margin allocation and design margin optimization, where we're trying to minimize this excess, subject to some minimum reliability, where the decisions are very complicated about what concept and in what sequence, because it turns out when you're doing the thermal analysis of residual stresses and all that stuff, it matters, how to optimize this, okay? And we also do it over epochs, over time, because the reliability requirements may change. And we're trying to find out what are the best strategies for this approach of design margins to work. And we don't come up with one solution. We come up with information to the designer in terms of trade space exploration. So if we have here weight, and we want to be as light as possible, and we have to here capability, we want to be as light as possible, you see that we have Pareto front. So we can distinguish between robust solutions, between Pareto optimal solutions, and between reliable solutions. And again, whether a designer in a particular industry and under particular regulations will go for flexible solutions or Pareto optimal solutions or robust solutions that are not Pareto optimal but are more secure, it's a different thing. What we can provide is the quantitative information. What they're going to choose at the end of the day, it's their prerogative. Right. So, second or last topic before I discuss our current efforts. Model selection. So I mentioned that the models that you use to predict and to compute the functions of interest are very important. And as you navigate big spaces, you find yourselves asking the question, which model should I be using if I have a choice in this particular area? I have an example here that shows, for a very, very simple cantilever beam problem, 3 methods, right? The Euler-Bernoulli model for the beam, the Timoshenko model, and an ANSF model. And you see that for this simple cantilever beam design problem, I have the predictions of the constraints in very different areas. And the constraint, of course, is active and it's driving my design. So if I use the ANSF model, my optimum is somewhere here. The Timoshenko model is somewhere here, and if I use the Euler balloon, it's somewhere here. So what is true? What is an adequate model for me to use? Well, of course, my model selection is also relative to my application. So we came up with our own philosophy, if you like, and we said, we will call a model adequate, okay, if its predictability is acceptable in relation to its computational cost for a particular application. And if we have multiple either physics-based or data-based models, or both, how can we select the most adequate model as we explore, again, like I said, as we explore the design space? Because at some point of the design space, one model may be adequate enough, in another not. So what we do is we first create a pyramid of model instantiations. So we have a phenomenon, the beam deflection, like I said before, very, very, very easy, or simple. We have three approximation models, Bernoulli, Timoshenko, ANCF. Then we have different numerical models to solve these models, right? And then we have parameters in these numerical methods, in different numerical methods, that will determine how you're going to solve it. So you have all these different model instantiations theoretically for a very simple phenomenon. Okay. Now what we do, and let me run it by use a running example for that. Let's say you simply have airfoil shape optimization. You want to minimize the lift, which depends on the coefficient of pressure of a given design over an airfoil, subject to some geometric constraint, and to drag, which again depends on the coefficients of pressure, not exceed some number. So we have transonic flow, let's say, over this airfoil. Right? This is the numerical grid. Zoom in, there's the airfoil. So let's assume only two models, TSDA and Euler-Inviscid adiabatic steady flow. Right? So only two mathematical models. And here we're going to do two different numerical methods for each. And then we have different parameters in the numerical method, like step sizes, termination criteria, and things like that. So at the end of the day, we have seven models, excuse me. We're going to pick one of the seven models, and this can be arbitrarily, but what we usually do is we say, okay, the most expensive model is expected to give the best results, which is not necessarily the true, right? The most expensive wine is not always the best, right? I guess you know that. Excuse me. So, but anyway, we use a reference model. Using this reference model, we compute the discrepancy of all the other models relative to this one, right? So these are the errors of the remaining six models to the reference. But we also compute the relative discrepancies between themselves, the other six models. So that gives us a matrix with zeros on the diagonal. And now we have a trust region approach. Again, if you're familiar with optimization, I hope that makes sense. Trust region means certainly you operate in an area where you trust your models. Okay. So let's say this is a design space. This is a simple schematic. This is not a real, we just did it for illustration. You have a design space with isocontours of the objective and several points. Let's say you're here. You evaluate your relative adequacy matrix, and you see that, for example, if you consider only one reference models and three additional models, you have the trust regions being here, and you run your optimization, and you see that only one model stays within the trust radius, so you pick to work with this model, because the other two exit your trust region. So you select to work with that model. Then you apply your derivative-free optimization technique that is illustrated here. You get to another point. You continue to use these models because the others still are outside. But at some point, you get out of it too, and another model becomes more reliable or adequate. So you switch to that model, etc., etc. Okay? So here, we run this. We have, in our example, the seven models, the reference model that has been used only in the beginning. And then you see that the most expensive model and most accurate one is not being used later on. We switch to other models. This gray scale shows how often we use a particular model as we explore the design space. We ran this problem for different sizes of variables, and it's an easy thing to do with airfoil because you can have different control points. Okay. And for different numbers of variables. And we can show here that we actually have a plateau of the number of model evaluations as you go to higher dimensions. So our computational cost for this methodology does not explode. While the benefits, this is cost ratio, how much we spend as opposed to having only one model, in this case the reference model. And you see that we always save between 85 and 80% computational cost. Okay, so that was the existing work. I think I have 10 more minutes. I'll try to show you in less than 5 minutes what we're working right now. It's going to be very high level. I just want to mention it. The first one is the cache problem. You know, these models that I'm talking about now, we're shifting to more and more advanced machine learning models. And the problem is not only which one to use, but also how to optimize it for performance. And it turns out that this can be viewed as an optimization problem, okay? And I'm going to go a little bit faster than that, excuse me. So far, people in the literature use the all-in-one formulation, everything lumped to solve this problem, but it has categorical variables, it has discrete variables, it has continuous variables, and we are applying our distributed optimization to separate so we can use a categorical algorithm for the categorical variables, a discrete optimization algorithm for the discrete variables, and a continuous algorithm for the continuous variables. So these are all just fancy, impressive math that just represent our augmented Lagrangian coordination technique. And we have compared ourselves to two public available machine learning database, not database, but tools, Optuna and Kokkolaras, if you like them. I think Kokkolaras out of A&M. I think Optuna is a non-profit organization. And we use it on a MNIST problem. It's imaging, image recognition matching problem that's available also publicly in the literature. And on the right is always our solution, distributed MDO with the alternative directed method of multipliers. And on the left is the various tools that Optuna and Kokkolaras have to offer. And as you'll see, here's the accuracy. You want to be as close to 1 as possible. And here's the cost, how many function values it got you to get to a high accuracy. And you can see that we are always doing better in either accuracy or cost than all the other methods available. This is still preliminary work. We are in the process of trying to get it published. But it's a very promising solution of the cache problem using our distributed technique. Then we're looking also at Bayesian optimization, how you adapt your models as you go. And a big problem is, remember when Simone said that they don't get answers from 80% of their evaluations and the empty spots in our example? Let's say here you have an area where simulations are failing, all right, but the optimum is in here. Your algorithm does not want to reach this area traditionally, and we have to reformulate the formulations of the Bayesian optimization problems. Here is an existing Bayesian optimization technique from the literature, cannot get there, but we changed the acquisition functions and we did some other tricks, and we actually did get there. Again, this is ongoing work, preliminary, not mature enough, but promising. We're also working to combine generative design that gives you tons of designs solving the inverse problem solely based on data, not physics. But we are introducing now physics-informed neural networks to actually filter the amount of solutions we get from generative design approaches. Again, this is something very preliminary. And finally, we have we're working on digital twins. We have a project that we just started with Hydro-Quebec. Hydro-Quebec is the power generation company in Quebec, the province of Canada where Montreal is. Certified 97% green. Certified, that means in reality it's even more, because it's all hydro. The problem is that they have very old and very large turbines. It's extremely costly to build them, operate them, maintain them, etc., etc. And all these years they have been developing models to understand how can they shut them down and turn them back on according to demand, which is a very, very costly thing to do, and also strains the turbines. And it turns out that for some reason, and that's why they came to us, the models fail to predict what's going on. And this is their current methodology, how they're trying to match their models with data that they get from very small time windows where they can shut down the turbine and measure things. And we're actually figuring out that this boils down to very simple, not simple, but to calibration issues with their model parameters. And we have started the investigation about how to help them improve the digital twins. So this is extremely preliminary work, but where digital twins will get us one day, from my understanding, is that you want to actually have them converge the virtual model together with the physical model at some point, and they exchange information almost simultaneously, and they become real twins. Right now, they are not synchronous. Right now, they exist in parallel universes, so to speak. All right. That's it. Final remarks. I wanted to emphasize that engineering design is a decision-making process. You make decisions again and again at every stage of the design process that we did not even analyze here. Therefore, it is subjective. It's always a design engineer who makes his decisions according to their best knowledge. And so, according to their best knowledge means that they need information. And optimization, at least in engineering design, my claim is, and my belief is, that is not going to give you an answer. You should not look optimization as something that will give you one answer for an engineering design problem. It will give you a lot of quantitative information that you have to assess based on modeling approaches, assumptions, etc., to make more informed subjective decisions as a designer. And with that, thank you for coming here. Thank you for inviting me. Thank you for investing your time to listen to my talk. There is a few minutes for questions.
Great, thank you so much, Michael. Any questions for Professor Kokkolaras? I definitely enjoy the second bullet that you have, that we are the decision makers. And I want to emphasize that we are the decision makers, not ChatGPT, because nowadays ChatGPT tends to substitute our decision making process. So any questions? Yes?
I can get started. So Michael, great talk. I think in the earlier slide you compare, the multidisciplinary, when we have the sub-problem, you have compared, NI versus NO.
Yes.
Can you get back to that
Yeah.
slide very quickly? I feel that slide is very inspiring.
No, yes, it was here.
Yes, this one. So when I look at that, I was so of course this NO versus NI comparison, how fast they converge, right? To that, I think it probably depends on the partition of these sub problems.
Right.
How you partition these sub problems, and also how strongly, or even the coupling relation, what kind of nature of coupling. So I'm just saying here why you are showing this, but I guess probably with a different kind of compute value allocation with a different problem, this trend could be different.
You're absolutely right,
reverse.
and that's why I emphasize that this is an empirical study.
Yes. Yeah.
And it absolutely depends on how the problem has been partitioned. Sometimes the problem appears to us in all. I mean, we have to draw the lines,
Yeah.
but it's obvious how it is partitioned. But I very recently completed the project with Thales, where they have a very nice tool. It's called MyCID. It's a functional representation tool, where they create graphs of how their subsystems are interacting.
Yes.
And they can create different, and then they can orient these graphs. And there's not a unique orientation. So they can create different partitions, as you said, and orientations of the problems that you can apply this. And we have not studied yet how performance depends on these different partitions, but that would be the next step. You're right about that. So we need to look at, if you're able to have different partitions, which one is the best?
Yeah, that's kind of the performance. And also I was wondering, depending on how you organize these numbers, would they, assuming that if the object function
Mm-hmm.
is kind of not kind of just a single object, so when you arrange different numbers of these kind of
Right.
loops,
That-
will they lead to the same
Right.
optimality?
So the local problems have their own objective functions. They're not necessarily, not every problem has to have an objective function, but they can have their own objective functions. In that case, you essentially have a multi-objective problem. And when you solve this once, you only get one Pareto point. Then you would have to alter the weight of the different local objective functions in different local problems to get another Pareto point. So, if I understood your question correctly, this is just one possible solution.
Okay. Yeah. Thank you.
Yes.
So may I have a question about this slide as well? So I saw that in the flowchart you have multiple subproblems.
Mhm.
You solve the subproblem in sequential manner.
Not necessarily. If you have an advantage if you solve them sequentially because you can also update information as you go on. You can solve them in parallel, but usually we have seen that when you solve them in parallel, you need even more iterations because the information update is not as rich as with sequential.
So that means we can solve it in with parallelization.
Theoretically, yes.
Yeah. Okay.
Yeah. But it may take you longer to solve. Yeah.
Any other questions for Professor Kokkolaras?
Yes.
I was wondering if you could explain how the trust region worked again.
Yep. So this is a
and
schematic.
The difference of selecting the model versus running the model till it leaves.
Right. So we start at some point. We create our relative adequacy matrix, the relative discrepancies between the models themselves. Then we have an inner mechanism about how the trust region is being updated using, nonlinear programming results. And as a schematic, here's our inadequacy space, and we say, okay, as long as we are within this trust region, okay, we're going to be fine. So you see what's happening at your first point when you try to solve, and you see that these two models want to get you to a point where you cannot trust the models anymore. So you select to work with this model and you conduct optimization iteration. Always making sure that you stay within here. Then you go to your next point. Sorry?
Are those axes the design variables or?
No, these are the errors.
Okay.
The relative errors for, and we have, thank you for asking the question. We have one error axis that represents feasibility for the objective function, and one for aggregate for all the constraints. Because in design, it's extremely important to, the trade-off is between what is optimal but what is feasible. And these are the main two errors that we examine. Yeah, thank you for the question. Allowed me to explain this.
Could you give us a picture of what proprietary software packages like ANSYS, what sort of algorithms do they use, and if the research
For analysis or optimization?
For optimization.
Okay.
And
They keep them secret, so they say what is the method of moving asymptotes, for example, or but we don't know the inner workings. These are proprietary. I mean, I have a student who works for Siemens and their HITS team, and she cannot tell me anything about their magic Sherpa algorithm. So I cannot comment on commercial packages and how they deal with it.
Do you think the research is ahead of them, or is the opposite?
Oh, that's an eternal question. I never know if we're really ahead of.
Because we don't know the state of them.
Right,
Because we
right.
don't have access to what they have.
I mean, like I said, for the airline problem, right? I mean, I don't know whether this is really relevant to them. Maybe they have solved it before and they don't care about it.
So I tend to overestimate the capacity of industry before I went to industry. But after I went to industry, I started
Yes,
to
I
realize
agree.
that this is not too sophisticated.
But it depends also. It depends also on the company. It depends on the domain. I mean,
Yeah, it all depends. Yeah.
Yeah. I'll give you another example if we have 1 minute.
Of course.
Am I over time?
Absolutely.
Not example, but I had a student. I didn't include it in the talk here. I already went over time. I had a student who was passionate about biomedical applications. So long story short, I'm not going to. He did work on optimal design of nanoparticles for drug delivery, especially for cancer treatment. So he developed the models, he developed the strategy, he showed me that there was a very nice trade-off between toxicity and concentration and the distribution of the drug. And he said, let's publish this. And I was telling him all the time, are you sure this has not been done? I cannot believe that somebody else did not do it in the life sciences, right? And he said, no, I have not seen anything. So we sent it to a journal where I went completely unknown. And I was waiting to be, slapped in the face. Who are you to tell us? And we got back. Very rarely it happens. He says, this is amazing work, accept it as is. We have never seen anything like that. I sent my student to the States, because we are in Canada, to 2 conferences. He had huge attendance in his talks. People wanted to collaborate with him. We collaborated with people. They gave us better models for tumor growth and everything. We published 3 more papers. He went on to Moffitt Cancer Research in Florida as a postdoc. And now he's faculty at Harvard Medical School, working on artificial intelligence approaches to
That's a great story.
to healthcare. Yeah. So we were ahead, and we did not know that. I couldn't believe that we were ahead.
Right, that's a great story.
Yeah.
Yeah.
It's not industry, but it's.
Great.
But I only have this one story to tell. I don't
That's a great story.
At least I have one.
Okay, guys, let's thank our speaker
Yeah,
again.
thank you for your time.